Hello, everybody. Today we're going to continue notes that we started yesterday over Chapter 3. Today we're going to also focus more on Section 3.2, talking about the different parts of an atom. So yesterday we discussed what the week's going to look like. So quickly, I'm going to show you the activity we're going to be doing on Friday, talking about Rutherford's experiment, which we will do in class and we'll talk about today. So for the Rutherford activity, you're going to get this worksheet. You're going to work with the people in your group. So what you're going to be doing is basically the gold foil experiment, but in a more friendly environment, using marbles and cardboard boxes. So the main things to take away is this procedure section down here, where it says you're going to be working in a group of 3 or 5. You're going to be working with the people at your table. And you need to divide up the duties because you only have about 45 minutes to work, 40 once we get everything explained. So you have to work quickly. You have a lot to do. Then you need to place the box on the floor directly by the lab station. So it'll just be right off the edge of the lab station. And I'll show you that on Thursday quickly. You're going to gently roll the marble off the end of the table. So you'll be going basically horizontally on the tables depending on which way you're standing. So across the lab tables to allow it to hit the box. So you're going to tally the number of marbles that directly hit a hole. So we count that as a hit. And then the ones that hit the top of the box and roll off would be a miss. If a marble does not do either, it doesn't count as your total. So the reason you have to do this kind of quickly and divide their duties is because you have to do total of 50 hits and misses together. So that what that means is 50 total rolls. But if it doesn't hit the box, it doesn't count. So if it doesn't go in or hit the lid of the box, it doesn't count, so you have to re-roll. So I always tell groups have about 2 people rolling, and then you have one person kind of catching marbles and pulling them in and giving them back to the rollers, and then you have like 2 people tallying hits and misses. And again, not 50 of each, 50 total together hits and misses. You will also want a calculator because you need to do a few calculations. I will have rulers out for you because you need to measure some things, because there's some other things you have to do first before it's done before the end of the period. Because if you get home and you don't know, so for example, number 1, calculate the total area by measuring the box length and width. If you don't know that, you'll be in trouble. Same thing with the diameter of the hole, because each box is different. And so you tell me which box you had, and so I can then verify. You're also going to solve for percent error, and then how does this relate? So just be ready to come in on Thursday to do this lab and to get everything done. Now, we are rolling marbles. If things get out of control, I will have you sit down. You will get a 0 in the lab, and it's 15 points. Do you really want 0 out of 15 points in the grade book right before conferences? I'll let you decide on that. So, be mature, do what you're supposed to do, get in, get out, get your calculations done so that you don't have homework over your nice long weekend. Okay, so that is our activity for Thursday. Let's get into notes. Okay, so yesterday we talked about the cathode ray tube and J.J. Thomson. So the cathode ray tube was deflected of a magnetic field. So the conclusion was that these deflected particles are negatively charged. So we found out based off the overall mass and that it's much lighter than a hydrogen atom, that it has to be some sort of particle that has a negative charge. So J.J. Thomson in 1897 measured the ratio of charge to mass of particle and found them to always be the same. He later proposed something called the plum pudding model, which was his idea of what an atom actually looks like. It will soon be proven wrong, but it's a solid start. So for conclusion, all cathode ray tubes are composed of identical negatively charged particles called electrons. So J.J. Thomson was the first guy to come out and figure out the first subatomic particle of an atom. So this is an example of the plum pudding model. So to the left is the English dessert called plum pudding. Obviously, it's not a pudding. It's like a bread, but it has raisins in it, and those raisins are what they use as an example of the electrons in a positively charged body. So on the right, you can see the kind of example that it's showing. Some people also like to call it like the blueberry muffin model, just because that's more of what we can relate to instead of plum pudding. So overall, general idea is on the right track, but we also know that we have protons and neutrons, not an overall positive body. Okay, then we talked about the charge and mass of an electron. So Robert Millikan in 1909 measured the charge and mass of an electron to be 9.109 times 10 to the negative 31st kilogram. So times 10 to the negative 31st, that is teeny, teeny, tiny. So that's why when we try and figure out the overall mass of an atom, we actually don't really worry about the electrons because their mass is so teeny tiny that it's really insignificant when it comes to the overall mass of the atom. Infrared from the discovery of the electron. So because of atoms are neutral, they must also contain a positive charge to balance out the negative. Because electrons have such a small mass compared to atoms, atoms must have other particles to account for that remaining mass. So we know the mass of an atom, like I said yesterday, hydrogen was 1.01. We know that. Well, if electrons are so light that they don't really have a mass to them that we calculate, there has to be something else in it, probably positive, to balance out the negative to give it its overall mass. But what is that particle? What does it look like? How does it work? And so it took us a little bit to figure out that it would be protons. So we have a scientist by the name of Ernest Rutherford conducted an experiment called the gold foil experiment. You're going to be doing a kind of off-brand version of that on Thursday. So what it is a bombardment of a thin piece of gold foil with a fast-moving alpha particle. Alpha particles are positively charged molecules that is shot into the gold leaf. Most of the alpha particles passed through, while a very small percentage were deflected. And so he was sitting there and he's like, why are some being deflected? It makes no sense. In theory, it should just go all the way through. So he created a conclusion after his experiment that atoms contain a dense positive core that he termed the nucleus. And he said atoms are mostly empty space, which we have then found out to be pretty much true. James Chadwick came in 1932 and proposed that there was a third subatomic particle that he called the neutron. And again, we figured out the overall mass of a proton is about 1. And so we're like, there's not that many protons in a mass of this atom. And so there must be another particle or subatomic particle that is within it. So we're like, let's call it a neutron. It has no charge, but it just helps add mass and balance out the internal nucleus of an atom. So here's a quick video that shows the gold foil experiment. Just a heads up, there's kind of annoying dinging noise that happens throughout the video. Sorry, it is what it is. Just watch it and then you don't have to worry about it anymore.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom by comparison is very big, so it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Alright, so that is the Rutherford gold foil experiment. That's pretty much what your activity on Thursday is going to replicate, as in the marbles represent the alpha particles going through or rolling towards the quote-unquote gold leaf, which would be the lid of the box. If it hits the lid of the box and ricochets out, then it would be it hitting the nucleus of the atom. And then if it goes right through to the bottom of the box, that would be it going through the atom of gold and not hitting anything, just the empty space. Okay, so important things to know. Protons are positively charged. Neutrons are neutral or have no charge. And the number of protons always equals the number of electrons. When we have a neutral atom, protons will equal electrons. Eventually, later on in the year, we will talk about if there's not an equal number of protons and electrons. But for now, all we need to worry about is protons equal the number of electrons. Okay, so let's talk about the structure of an atom. So an atom is the smallest particle of an element that retains the chemical property of that element. And again, every element has its atom that represents it. So atoms contain 3 subatomic particles: protons, neutrons, and electrons. Protons and neutrons are found in the nucleus of the atom, and the nucleus is held together by nuclear forces. So short range, proton and neutron, proton to proton, and neutron to neutron forces. So these nuclear forces are so strong that it basically stops the atom from trying to explode and kind of break itself apart, because we know 2 positive ends of a magnet repel each other. So in our idea, protons would try and repel each other, but these nuclear forces are so strong, they hold it together, and force it to be right next to each other. So here is an example of what an atom would look like. This is what we call a Bohr's model. So this is a carbon. So carbon has 6 protons. So those are what are there in red. A lot of times they're represented by a P or a plus sign or a P with a plus sign as an exponent. Either way is fine. They're always found in the nucleus in the center. Neutrons are either shown as empty, or they'll be shown as a lowercase n or a 0. That means there is no charge, or they're neutral. And then outside on the orbital rings that are green, those are our electrons. The inner ring can only hold 2 electrons. That's why there's only 2 on there. And then that next ring can hold a total of 8. So we start from the inside, put our 2, go to the outside, and we have 4. And that's why carbon can make 4 bonds. So a lot of times with electrons, you'll see me represent it by an E with a little negative sign as an exponent. Sometimes people show it as just the negative sign. Some people just leave it as the letter E. Anyway is fine, but I need to be able to know which one you're talking about. So there needs to be some key or a way that I know which subatomic particle you have drawn if I ever ask you to draw these atoms. Okay, so quickly we're going to watch a video about how we keep these nuclear forces together.
So that's one half of the story of electromagnetic charges, electromagnetic attractions and repulsions. That was attraction of opposites. Now we've got the repulsions of like charges, and that creates a problem for us. Let's just think, we're all sitting here quite happily, nothing untoward happening to us, not exploding or anything. But inside us are atoms, and in the middle of the atoms are nuclei, and here is an enlarged picture of a nucleus with lots of neutral particles in it, but also lots of protons, each one of which is positively charged. Now, like charges repel. So each of these protons is repelling all the other protons. The nucleus then should be exploding apart, yet somehow it stays together. Now that's a puzzle. We'll come to that in a moment and find the answer to it, but first of all, let me give you an idea of actually how strong that repulsive force is. Bryson's next demonstration is going to show us the repulsive power of electromagnetic forces. So, what we're going to do now is first of all cool down this ring so that we make the effect rather more dramatic. And we've got a magnet here which will turn on when Bryson throws the switch, when everything's ready. Okay, don't spill it over me. This is about as cold as, well, the universe out there now. Are you all ready? Oh, this is going to be really dramatic by the time it gets going. Right, here it is. Ready to go. Put it on the magnet. Now, turn the magnet on. Okay, do you reckon we'll try it again? Well done. So, you saw there the power that magnets have got when you can make things repel. In fact, it sent the thing almost as high as I came down from at the beginning, and then it came down rather faster than I did. So, that's the repulsive power that you saw there with a large-scale magnet. Just imagine now, then, the strength of the repulsive power buried in the nucleus. These things are really small, pretty well touching, and each of them repelling with at least as much power as you just saw. So how come we are still sitting here happily without our nuclei exploding apart? There must be something very, very strong here, another force, a very strong force gripping the nucleus together and overcoming that repulsive power. Let me show you what we believe today that's caused by. So here is a picture of a nucleus opened up, and you see the 3 quarks buried inside one of them. And the strong force that binds the quarks together is shown here by these little wiggly lines to give the impression of the things really being gripped. Now, this force is so strong that it leaks out very slightly. We show this on the outside here, and grips the individual neutrons and protons together. So it's that very strong force, rooted in the quarks, that holds the nucleus together and resists that outward thrust that we saw the demonstration of.
All right, so there's that quick explanation as to how that nuclear force holds that protons together and those neutrons together and doesn't allow them to try and spray outwards and explode the atom completely. Okay, so main things to take away. Electrons, symbol is E with a negative X or negative sub or exponent. Has a -1 charge and it's always found outside of the nucleus. Protons, represented by a lowercase p with a plus sign as a exponent. It always has a +1 charge and it's found in the nucleus. And then a neutron, represented by a lowercase n with a 0 as the exponent. It is a charge is 0 or neutral, and it is also found in the nucleus. All right, so that's all I have for you today. Make sure you're working on any missing work, and when you're done, make sure your notes are completely filled in. Find something to do to keep you busy for the rest of the class period. If you have any questions, please let me know. But I will see you on Thursday. Have a great rest of your day. Bye.